So now we're on to maximum power transfer theorem. We're going to apply the maximum power transfer theorem to determine the value of load resistance for which maximum power is transferred from a given circuit. So when we look at this, the maximum power transferred to the load is when the internal resistance matches that of the load resistance. So we have perfect matching, or as close as we can get to perfect matching, when these two resistances match each other. So let's look at an example here. We've got a circuit, it's got a 10 volt source, it's got an internal resistance of 75, and we're going to change the load resistance 25, 50, 75, 100, and 125, and we're going to match the output and see where we got the maximum power transferred. Again, the idea behind this is determining how we match something like a speaker to a stereo system so that we get the maximum amount of energy without distortion or without loss going from the amplifier into the speaker itself. So let's take each one of these one at a time. So we use Ohm's law, I equals V over R, and the power formula, power equal I squared R, to find the load power. The load power for each value of load resistance then will be calculated. So for a load resistor of 0 impedance, 0 ohms, so we have I is equal to V sub S divided by the series R sub S, R sub L, the internal resistance and the load. So 10 volts divided by 75 ohms will give us 133 milliamps. Okay, so for that, if we'd use our I squared R relationship, then 133 milliamps squared times 0, of course, is 0. So we have no power transferred to the load when the load resistance is 0. Okay, that means it's a wire. So let's up it to 25 ohms. So at 25 ohms, we have 10 volts divided by 100 ohms, and we get 100 milliamps of current. So I squared R, 100 milliamps squared, 25 ohms, gives us 250 milliwatts of power. So we're starting to pick up. Now, if you're going to see a graph, you're going to see that graph start to come up. Let's increase it to 50 ohms. So 10 volts divided by 125 ohms, 80 milliamps. I squared R, 80 milliamps squared by 50 ohms, gives us 320 milliwatts. So we can see the power is starting to creep up. 75 ohms on the load. So V sub S, R sub S, R sub L gives us 10 volts by 150 ohms, or 66.7 milliamps of current. I squared R, 66.7 milliamps squared by 75 gives us 334 milliwatts of power, okay, to the load. So now let's see what happens when we put 100 ohms. When we put 100 ohms on the output, we have 10 volts divided by 175 ohms total, which gives us 57.1 milliamps. But when we take our I squared R, 57.1 milliamps squared by 100 ohms gives us 326 milliwatts. So it's starting to bend down. And then lastly, 125 ohms. So we have 10 volts divided by R sub S by R sub L, 200 ohms gives us 50 milliamps. Our I squared R relationship, 50 milliamps squared by 125, gives us 313 milliwatts. So we came up to 334. We probably flattened out a little bit, and now we're coming down on the other side. We're losing power. So notice that the load power is greatest when the load is 75 ohms, which is the same as the internal source resistance. When the load resistance is less than or greater than this value, the power drops off, as the curve here will indicate. So you can see we came up, we came up, we came up, we hit some maximum point, maximum power, R sub L is equal to R sub S, and then it starts to trail off again. Okay, so this is what maximum power transfer shows us. It shows us the point where the internal resistance matches that of the load. And when we do that, we get the maximum amount of energy out into our load. Again, if it's a speaker, then you're going to have the maximum amount of energy delivered to the speaker without distortion. So in the next section, we're going to look at something called delta to Y and Y to delta conversions. The idea behind these conversions, and we're not going to go into it, but if we have relationships where it's difficult to solve the analysis in, say, this delta, there is a way where we can mathematically convert A, B, and C to 1, 2, and 3. So when we come back, we're going to look at Y to delta conversions.